Welcome to The Explainer. Today, we're diving into this really powerful way of thinking that, honestly, you're probably already using without even knowing it.
So let's just jump right in with a question. What could possibly connect map making, game design, and 3D animation? I mean, on the surface, they seem like they're from totally different universes. But there's a hidden thread, a shared way of solving problems that actually links all of them together.
The answer isn't some fancy software or programming language. Nope. It's a very specific and really powerful way of thinking. It's a mental framework for tackling complex stuff that came out of computer science, but you can apply it, well, pretty much everywhere. And it's got a name: computational thinking. This is the secret ingredient. This is what connects our three different worlds. And you know what? It's a skill that's becoming absolutely essential for everybody. Okay, so what is it exactly? Let's get a really clear definition here, because this is not about turning you into a programmer, not at all. It's about giving you a new lens, a new way to see and solve problems.
So researchers at DePaul University put it this way. It's the set of skills you use to apply computational techniques to projects in any field. And those are the keywords right there, any field. This is a universal thing. Whether you're an artist, a scientist, it doesn't matter. In fact, Jeanette Wing, the computer scientist who really popularized this whole idea, she just nailed it. She called it a universally applicable attitude and skill set that everyone, not just computer scientists, should be eager to learn. Everyone! So if this is such a universal skill, how do we get our hands on it? How do we start using it? Well, those same researchers from DePaul came up with a fantastic way to think about it, as a universal toolkit. They built this toolkit around what are known as the 7 great principles of computing. You can almost think of them as 7 different hats you can wear, or 7 different angles you can use to look at and solve a problem. So, the toolkit is built on these 7 core ideas: computation, communication, coordination, recollection, automation, evaluation, and design. Now, to really see how this works, we're not going to go through all 7. We're going to zoom in on just one of them to see how powerful it can be. Okay, so let's focus on that last principle, design, because this is the key. This is what's going to unlock that hidden connection between our map makers, game designers, and 3D animators. The design principle is really all about one thing: managing complexity. It's about using tools like, say, abstraction, which is just a fancy word for simplifying a big idea, and modularization, which means breaking a problem down into smaller, reusable chunks. Let's see it in action. First stop, the world of mapmaking, or geographic information systems. And the challenge here is huge. How do you take the real world, which is infinitely complex, and represent it accurately inside a computer? Okay, check this out. Say you need to represent a lake on a digital map. A vector model uses points and lines to draw a super precise boundary, perfect for showing exactly where the land ends and water begins. A raster model, on the other hand, uses a grid of pixels, which is much better for showing continuous things, like maybe elevation or water temperature. Both are totally different approaches, but they are both forms of abstraction. They're simplified models of a real lake. That's the design principle right there. All right, now for something completely different. Let's jump over to game design. And here, we're not talking about just the rules you read in the box. We're talking about digging deeper and understanding the hidden structure of a game. This is honestly one of my favorite examples. On the left, you've got tic-tac-toe. We all know it. On the right, a different game. Players take turns picking numbers from 1 to 9, and the first person to have 3 numbers that add up to exactly 15 wins. They seem completely different, right? Well, they're not. Their underlying mathematical structure, what game designers call the constitutive rules, it's identical. They're the same game in disguise. That's thinking about game design, not just the surface-level rules. And for our final world, let's pop into 3D modeling for movies and video games. The big problem here is creating these massive, detailed, believable environments without having to literally handcraft every single leaf on every single tree. So how do you build a realistic field of grass? You don't sit there modeling millions of individual blades. No way. You use design. First, you modularize. You create one single, perfect blade of grass. That's your module. Then you automate. You get the computer to copy and paste that blade thousands of times. But that would look fake, right? So the last step is to randomize. You automatically tweak the position, the size, and the color of each copy to make it look natural and organic. That's how you build a complex system from one simple piece. So we've just seen one principle, design, at work in 3 completely different fields.
let's zoom back out and connect the dots. What does this all mean for you and me?
This slide really ties it all together. The common thread, that hidden link, was the design principle all along. Map makers use abstraction. Game designers analyze structural logic. 3D modelers use modularization. It's all just different flavors of the same core idea.
And that right there is the big takeaway. Computational thinking is not, I repeat, not about thinking like a computer. It's a deeply human skill. It's about using this incredible toolkit to take big, messy, complicated problems and break them down into something you can actually solve, no matter what it is you do.
So I'll leave you with this question to chew on. Think about it. When you organize a huge to-do list into smaller, manageable tasks, or when you create a recipe to cook a meal, or simplify a really complex idea to explain it to a friend, you're already doing it. You're already thinking this way. So the real question is, where else could you apply it?